Lat 3 magnetic field of permanent dipole magnets. In a small bar magnet, we can experimentally and computationally find the distance dependence of the magnetic field. The results of this experiment will be compared to the distance dependence predicted by the equations for the on and off-axis magnetic fields derived from the Biot-Savart law. We have divided this experiment into two parts: the distance dependence of the magnetic field of the bar magnet, and then the off-axis magnetic field. The materials are shown. Earth acts as a big magnet, carrying a magnetic field whose components vary depending on your location, which is how compasses show the behavior that they do. The calibration procedure for the magnetometer app to align the Earth's magnetic east-west axis is shown. This experiment took place in Atlanta, Georgia, and the B net values will reflect this. For better accuracy, we're going to identify the location of the phone's magnetometer sensor by finding the location where the absolute value of the X component is at a maximum and the absolute value of the Y component is at a minimum. We're going to turn the phone and do the vice versa. The magnitude of the magnetic field due to a bar magnet decreases as the observation location is moved further from the magnet. The distances at which the X component of the magnitude approximately equaling 20, 70, 120, 170, and 220 were measured. 3 trials occurred for each magnitude, and the averages are shown below. Using the distance dependence results, the magnitude of the magnetic moment of the magnet can be found. We can determine the values by plotting the distance dependences, the natural log of Bx with the natural log of R. The magnitude of the magnetic moment of the magnet can then be used to calculate the magnitude of the moment of the magnet using this relationship, which we find to be 4.199. When the magnetometer is far away from the magnet, it measures a near zero magnetic field in the X direction. We observe as the magnetometer moves closer to the magnet, the measured X component of the magnetic field increases. In part 2, we're going to use the same experimental setup as part 1 and find the distance of the magnet on the east-west axis at which B bar equals 100. We're going to move the phone the same distance in the north direction and record the X, Y, and Z components of the net magnetic field and run 3 trials. We're going to correct the Y component of the net magnetic field to account for the Earth's magnetic field as shown below to find the average B net value. The experimental results from part 1 can be used to develop a computational model of the magnetic field on, perpendicular, and 45 degrees to the axis. The value of the moment of the magnetic moment that was experimentally derived will be used to determine B at these observation points using this relationship in the computational model, which is shown here, with the white representing the bar magnet and the arrows representing the various magnetic fields. The values of our experimental and computational model can be compared below. We find that while they are slightly off, they are fairly similar. If in the experiment we oriented our setup to compensate for magnetic north, if we hadn't compensated for magnetic north and instead laid out our meter stick at some intermediate angle with respect to Earth's magnetic field, our results would have changed if we hadn't accounted for this angle. The bar magnet would not be considered to be isolated as the Earth's magnetic field would be affecting it, and the B net value would ultimately be affected until corrected for. If we had 2 identical magnets and we redid the experiment, but instead of using a single magnet, used 2 identical stuck together end to end, we can expect our measurements to differ. The strength of the dipole moment would double, although not the charge, and the magnetic field would double accordingly, as the separation does. The glow script code is shown below.